Okay, zero fluff today. We're jumping straight into an autopsy of a mistake that literally bleeds marks in Cambridge IGCSE physics practicals. If you're sitting on a grade boundary risk right now, pay close attention. What we're dissecting today is the exact difference between a failing grade and absolute top marks in your 0625 syllabus. Let's get right into it. So take a look at this. A student gets a classic Hooke's law practical setup, right? And they confidently write this down. Change the weight and see how long the spring gets. Now, be honest, it feels intuitively correct, doesn't it? You add weight, the spring stretches. Makes perfect sense. But I want you to pause for a second. Can you spot the massive, grade-dropping terminology flaw here? Why does this exact sentence, which perfectly describes the physical reality, score an absolute 0 for experimental design? Well, the contrast here is honestly staggering. On the left, we've got our flawed, everyday language answer. But on the right, that's the top band, Cambridge-approved golden ticket. Force or load is the independent variable, extension is the dependent variable. This right here is exactly why ordinary revision completely fails you. You can understand the physics flawlessly in your head, but if you don't use the exact terminology the mark scheme demands, you get nothing. The examiner isn't testing if you know springs get longer. They want to see if you can systematically design a scientific investigation. So we need to totally rebuild your vocabulary. Section 1. Mastering physics variables. Let's lock down a fail-proof framework for any setup they throw at you. No more guessing, just quick wins. First up, commit this to memory, the independent variable. This is the variable that you, the experimenter, actively change. It's literally the very first thing you choose to alter. Think of it as the cause. In our spring setup, you're the physicist deciding to add 1 Newton, then 2 newtons, then 3 newtons of force. You are totally in control of that change. Building right off that, we have the dependent variable. This is what you're actually measuring or observing when you change that independent variable. It's the effect. You change the force, you step back, and you measure how much the spring extended. The extension literally depends on the force you just applied. If you mix these two up in your exam wording, well, the examiner is going to assume you have no idea how an experiment even works. And to complete the trio, we've got the control variable. This is anything you have to ensure stays exactly the same throughout the whole experiment. Why? Because knowing what affects what means you have to lock down everything else. If the room temperature suddenly drops or you randomly swap the spring for a different one halfway through, your data is totally ruined. You've got to lock those external factors down tight. Now, listen closely. You might be sitting there thinking, great, I know the 3 variables, I'm ready to ace this paper. Nope. In a moment, I'm going to show you a hidden examiner clue regarding data types that completely changes how you collect and graph your data in the exam. But first, you really needed this variable framework to make that clue obvious. Seriously, if you click away now, you're going to walk into your exam completely blind to a massive trap that catches thousands of students when they're asked to design a data table. Section 2, categorizing your exam data. Okay. This is where we take those variables and figure out exactly what kind of numbers or words you're putting into your table. Based directly on our source material, there are 3 distinct types of data you need to know. First, categorical data. Just like it sounds, this is data sorted into categories or groups. You can't really order it mathematically. Think of material names like glass, plastic, or water. Second is continuous data. This one can take absolutely any numerical value within a range. Temperature is the perfect example here. It could be 20 degrees, 20.1, 20.15. It flows continuously. And finally, discrete data. This is where your values can only be certain, specific numbers, usually whole ones, like the number of protons in an atom. You can't have half a proton, right? Knowing your data type up front completely dictates how you format your answers and graphs. Section 3, spot the error challenge. The stakes are rising, so let's apply this under a bit of pressure. This is a real Cambridge-style setup, worked example 2.1 from our source material. You're finding the critical angle as light emerges into air from semicircular blocks of different materials. I want you to pause and predict right here. Look at those blocks labeled A, B, C, and D. Based on our framework, what is the independent variable, what's the dependent variable, and what are their exact data types? Don't just sit there watching. Actively test yourself right now before I reveal the answer. Okay, let's break this down exactly how a top-tier student processes it in the exam hall. Step 1, decide the independent variable. Just ask yourself, what am I, the experimenter, choosing to change first? Step 2, decide the dependent variable. Ask, what am I actually finding the numerical value of each time I make that change? And here is your examiner style correction. The independent variable is the material of the block. You're swapping out glass for plastic or maybe diamond. And since those are names of materials, your data type is categorical. Boom. Now, the dependent variable is the size of the critical angle you're measuring with your protractor. Because an angle can be 41 degrees or maybe 41.5 degrees, it can take any numerical value within a range. That makes it continuous data. You see, when you combine variable identification with exact data types like this, that's how you secure the absolute highest marks, because you're proving deep scientific literacy to the examiner.
Section 4. The final exam check.
This whole exercise brilliantly illustrates our main goal, right? Moving from that vague change the weight answer to highly specific examiner grade structuring. But here is the massive unresolved problem we're still left with. You have the perfect theoretical framework now. You know your variables, you know continuous from categorical, but when that exam clock starts ticking and you have exactly 4 minutes to write a 6-mark practical design question, theory just isn't enough. How do you physically structure this knowledge into a perfectly timed answer under intense pressure without panicking? If you just sit with this theory, honestly, you're going to run out of time in the real exam.
Which means watching our next explainer is your absolute mandatory next step. On the left of your screen right now, you'll see our explainer on the Physics 0625 timed answer writing system. Click that immediately to learn the exact blueprint to write faster and secure every single mark. And before you do, hit the subscribe button on the right. Subscribe to our YouTube channel, Ace the Exams at acetheexams_IGCS to excel in your Cambridge examinations. Click the explainer on the left right now. Will your next answer secure full marks or cost you a grade boundary? Let's build your perfect timed answer over there. See you in a second.